Hello, welcome again. We are covering the subject thermodynamics for civil services mains, IFS, and various gate exams. And now we have finished the topic steady flow energy equation. Now we'll solve some questions based on that. Question number one is a hot ideal gas Cp is equal to 1.2 kilojoule per kilogram per degree Kelvin steadily flows through a turbine with inlet and exit temperature of 1500 Kelvin and 500 Kelvin respectively. The minimum mass flow rate in kilogram per second of the hot gas to achieve a power output of 12 megawatt is. So here we have derived the expression for work done in case of turbine, and that was the difference of outlet enthalpy minus inlet enthalpy. So if m is the mass, then the work done per second is, if the m is the mass flow rate, here mass flow rate we have to find out, then the work done per second is m mp bracket h out minus ht, and this h out minus ht is your cpt out minus cpt in. So cp is your 1.2 into 10 power 3, and t out is 1500, and t in is your 500, and work done per second is your 12 megawatt or 12 into 10 power 6. So here this 1.2 kilojoule, so we will convert it into joule, and if we will also convert it into joule per second, that is 12 into 10 power 6. So m is from this m comes out as 10 kilogram per second. So this is the answer. Next question, question number 2. Steam at an initial enthalpy of 100 kilojoule per kilogram and inlet velocity of 100 meter per second enters an insulated horizontal nozzle. It leaves the nozzle at 200 meter per second. The exit enthalpy in kilojoule is dash. So this is your nozzle. Nozzle is your adiabatic, so no heat is supplied in the nozzle. So C1 is the velocity at inlet and C2 is the velocity at outlet, and levels are same at the inlet and outlet, because no description is given about the level. So potential energy will remain same, no heat supplied, no work done, so the energy equation will reduce to h1 plus c1 square by 2 is equal to h2 plus c2 square by 2. So h2 minus h1 is your c1 square minus c2 square by 2, and c1 is velocity at the inlet, that is 100 meter per second. Enthalpy at the inlet is given as 100 kilojoule per kilogram, so 100 into 1000, and c2 is 200, so h2 is your 85,000 joule, because c1 is given, c2 is given, and h1 is given. So we will find out only h2. So h2 will come out as 85,000 joule per kilogram, or 85 kilojoule per kilogram. So that is your second question. Next question is question number 3. Two streams of air Cp is equal to 1005 per kilogram per degree Kelvin flow through insulated pipe 1 and 2 with conditions as shown in figure. They mix in an insulated pipe 3, and the mixture steadily exits with a velocity of 100 meter per second at 150 kPa. Neglecting the change in potential energy in the all pipe in the exit area of pipe 3 in meter square up to 3 decimal there. So this is the inlet of first stream of mass 1 kilogram per second, velocity 50 meter per second, and temperature 300 Kelvin. And this is the mass entering in the pipe 2. This is also in the mass is 3 kilogram per second, temperature is 400 Kelvin, and velocity is 30 meter per second. And this is the exit of the pipe. So these are the inlet conditions, and this is the outlet conditions. So applying energy equation between inlet and outlet. So energy at 1, this is inlet, energy at 2, this is inlet, will be equal to energy at output, and no work or no heat is supplied uh, within these pipes, and the level of this pipe is same, so there is no change in potential. So energy at 1 is uh, kinetic energy plus heat energy, so that is heat energy is mcp1 and kinetic energy is m1 v1 square by 2, and energy at 2 is m2 cp2 and kinetic energy is m2 v2 square by 2. So at 3 the total mass becomes mass entering here and mass entering here, that is m1 plus m2, and so temperature is T3, so m1 plus m2 cp3, and this will be your plus m1 plus m2 by 2 v3 square. Okay. So putting these values, m1 is 1, cp is 1005, p1 is 800, m1 is 1, this is 50 square by 2, and this is your 3 into 1005 into 400, and this will be your 3 into 3 30 square by 2, and is equal to this 3 plus 1 is 4, 4 into 1005 into 3, and this will be 4 into 100 square by 2, because here the velocity is given as 100. Velocity is 100 meter per second. So here using solving this for T3, because here only unknown is your T3, so T3 comes out as 495.67 Kelvin. Now pressure at P3 is given, that is 150 kPa. Temperature we have found out using a state equation P3 V3 is equal to N3 R3 R T3. So we can find out V3 because we know P3 and we know T3, we know M3. So V3 specific volume comes out as 379.25 meter cube per second. Okay, or it will be in meter cube per second because mass is in kilogram per second. So this is your specific volume, and now we can find out area also. Area is specific because volume, this is your volume flow rate, and volume is A3 into V3. V3 is velocity, and velocity is 100 meter per second. Capital V3 is velocity, small v3 is specific volume, and from this A3 will come out as 0.03795 meters square.